we're going to kind of finish up lecture 1 and talk about what we talked about in lab yesterday, which was actually technical writing. So big focus here in this class, especially in our lab component of this course, is technical writing and data analysis and being able to kind of communicate technical information to a wide audience, different audiences, and be familiar with different forms of technical writing, even though, again, in this course, unlike in Engineering 45 or other courses that I might teach, we are going to become experts in writing laboratory reports. But it's really, really useful to know, if you don't know already, kind of some of the different forms of technical writing. So we have executive summary, lab report. You'll be the expert in this guy. Or this is actually a technical memo, but it's a little bit interesting as well. Progress report, full technical report, technical paper. There's lots of distinctions here. So remember, we talked about yesterday in lab, executive summary. Again, usually 1 page. This could be no figures. And again, meant for high-level audience. So CEO could be a business person, could be a very, very general group leader of R&D. They don't know what's going on with your project. You have to keep the technical information to kind of a minimum. This is in really, really stark contrast to kind of a full technical report or technical report, which is when we're dealing with basically a full, it could be hundreds of pages long, lots of figures. It's meant for basically your kind of the colleague in the lab right next to you. And we use this document that full technical report, to basically reproduce results, reproduce experimental results. So it's kind of a guideline, and kind of a, again, it is what the name says, it's a technical document. So there's oral reports, poster presentations, just like we talked about last time in our kind of the lab component of this course, where we're talking about technical writing. So you all are experts in that at this point. The key thing I want to focus on, again, are just to kind of reinforce that we need to create high quality figures in this lab and in this course. So that's where you want to start that's where you want to start when you're designing your technical document, when you're writing your lab report. You should start with the figures first, generate really, really high quality figures. The figure should stand on its own. So your figure should just be able, by looking at it and by reading your caption, which goes below. The figure caption should be a couple sentences, so 1 to 4 sentences. You should just be able to look at this figure, read this caption, and understand exactly what you want to communicate with the purpose of that figure. So you need that. That's kind of a good tip to designing it. So make sure the graph is very easy to kind of understand and conceptualize, and that it makes sense, and that your description, that caption should say the 1 to 2 things that you want the reader, or you want the person reading your document to kind of take away from that figure. Because I don't know about you all, but when I read technical documents and technical papers, I look at the figures first, read the captions. If they're not interesting or they don't communicate the information, I move on to the next one. So that's kind of the thing that you want to think about as you move forward, and as you, again, you should stand on their own as you prepare writing your technical documents. But we'll have lots of time in lab to work on that together, so no worries on that. Graphical presentation of data. So again, there's rules and tips. Again, these aren't really rules. I'd say more tips and guidelines. So don't stifle your creativity, but these are some good information to have. So we must have clear labels and units. Primary information, clearly numbered, tick marks appropriate, use log, semi-log, scientific notation. Again, I know these are, should be fairly, intuitive and straightforward, but you'll see that there's kind of, I'll often kind of see some interesting things done on lab reports in terms of graphs and presentation of the data. Use appropriate scales. Symbols are kind of key to distinguish between, in our lab, we're going to be oftentimes we'll be comparing the theoretical result and the experimental. So you just use different square, circle, star, etc., open, closed. It doesn't really matter. Legends. In Mathematica, legends are hard to create, so I would suggest creating those in PowerPoint, so PPT. I'll show you again how to do that. Error bars are a must. Every plot that you present in this course, you should have, if it's an XY plot, I need to see an error bar here, and I need to see an error bar here. If it's too small to see, or if you don't think that there's uncertainty, you need to justify that in your explanation result. Lettering, again, minimal text. You don't want to get too wordy. Labels should be rotated, concise, descriptive. You don't have to have a graph title, But again, if you feel like it's necessary to, the most important thing is this first sentence. Graph should convey primary crucial information to reader without having to read the caption. So whatever you have to do, actually with reading the caption as well. If you could do this without reading the caption, that's a really amazing figure. But that should be your goal. So whatever you have to do to kind of reach that goal, that's what we want to do. So, grid lines, yes, get rid of grid lines, no grid lines. And yeah, that's pretty much all that we're looking at for here. So remember, read, before you start writing your lab report, read that document on Canvas, the technical writing guide. And if those of you that don't have access to the Canvas site and are interested, please let me know. Now, line fitting. We need to understand essentially how line fitting, or when line fitting is appropriate, and how to interpret this data. So one of the things, and we're going to talk about it more next time when we get into lecture 2, I see oftentimes students, and not only students, colleagues and researchers, again, not to bash the biology people, but a lot of biologists and chemists, everyone is really obsessed with, they see a data set and they want the highest R-squared value. They want R-squared to be equal to 1. And they'll do whatever it takes. They could do, for this data set, or actually I should start here. For this data set, even though, instead of doing a linear fit, people will do a 12th order polynomial fit in order to get a higher R-squared value. The question that I want to ask you is, what's the physical meaning of a relationship that is a 12th order or 20th order polynomial fit? It's not physical. It doesn't match with the theory that you're investigating in your experimental apparatus? Or does a 20th order polynomial fit have any physical meaning? No, there's so many fitting parameters that it just is not meaningless. So you have to fit an equation that matches what is the actual theory that you're working with. So if you're working with the Nernst equation, for example, for electrochemical data, a 12th order polynomial fit doesn't matter. If the theory is linear, you need to compare. Okay, do a linear fit. If R squared value is low, or if again, R squared value is not really important to us. But if there's deviations from your experiment in theory, you have to explain them. The data is the data. If you capture the data correctly, that's the data that you're working with. That's the experimental data. If there's deviation from theory, you need to be able to explain that. And if you did the experiment wrong, or there's some human error or some other things, or your apparatus doesn't have enough resolution, then you need to redesign your apparatus and redo the experiment. But you can't just fit differently to get a higher R squared value and think that you're done for it. So an R squared value in this class, I don't care about that. I mean, it has no meaning unless you fit correctly in terms of the theory, and then it has to have context in the experiment and the physical parameters you're trying to measure. That's kind of my key point. So please, so remember in this course, no percent error, never, no purpose of this lab, and no focusing on trying to get your R squared value better. This is not, it's pointless. I want trends. We're, as engineers, we're interested in kind of trends of the data set. Real numbers, or kind of the final number that you get out, it can be important for some applications, but for meaningful changes, for really new and amazing applications, we are concerned with orders of magnitude changes. We're interested in trends. The data can, that comes out at the very end. So don't be like biologists, or just focus on these R squared or ANOVA tests. We'll deal with that a little bit later. So keep that in mind. And finally, we're going to talk a little bit more about this, but one of the ways that you can improve the resolution and minimize your uncertainty and error in designing experiments is by kind of performing kind of this uncertainty analysis of precision and bias. There again, it's a little bit ahead of, we're going to talk about this a lot more, but you could kind of design and think about your experiment ahead of time in building your experimental apparatus and test to see what's the uncertainty. So if you have a target in mind, so if I want to measure, something like 10 to the minus 12 moles, 10 to the I want to do picomolar, or even could do femtomolar concentrations. If that's the resolution or the target I'm trying to hit for, I need to look at my apparatus, the design, and look at the uncertainty and see beforehand, try to estimate, am I even in this range? Or do I have to kind of redesign my experiment, find a better transducer, filter my signal, et cetera, et cetera, et cetera. So when you're measuring something, you want to have that target in mind before you design your apparatus, ideally, because you don't want to design an apparatus that's $10,000 and realize you've made a huge mistake and have to redesign the whole thing and tear it apart. So it happens in experiments, and it's not, There are often times when you think you have that resolution, and it turns out it's not, but you can kind of save yourself a lot of time and headache if you kind of do this ahead of time. So thinking about the design, performing some uncertainty analysis that we're going to talk about a little bit later in next lectures, and then move on from there. So that's it. We are at, that is lecture 1 completed. So lecture 1 done. We have 8 more to go. So I'll see you next time, and we'll get into some math and uncertainty and z-tables and some fun stuff. All right, see you next time.